So hey guys, welcome back to my YouTube channel. So in this video I'm going to explain the topic, that is another algorithm of graph, that is Bellman-Ford algorithm. So Bellman-Ford is kind of we can say similar to the Dijkstra algorithm, which is also a finding for shortest path, or we can say shortest path from the source node of from one node to every node of the graph. So Bellman-Ford is another we can say uh, algorithm which is used to find the we can say used to find the minimum distance from the source node to the all nodes of the graph. So this is the uh, algorithm which find the minimum distance from we can say from the source. We in this Bellman-Ford algorithm we have given the source node. Okay, we have given the source node, and we have to find the distance of minimum distance of that all the nodes from the source node. So this is the Bellman-Ford, but Dijkstra is also same, but uh, there is one limitation, or we can say a limitation of Dijkstra algorithm is we cannot this Dijkstra algorithm cannot work with the negative cycle, or we can say negative edges, weighted edges. So you have seen that in Dijkstra algorithm we are taking the weights in the positive, all positive, we can say positive, all weights in positive. So in Bellman-Ford, if we so Bellman-Ford is we can say used in the finding the we can say used in this negative edges also, and it is also we can say find help in detecting the negative cycle. Meanwhile, which is that is Dijkstra algorithm is not capable of finding the negative cycle in a graph. So there is huge advantage of this we can say there is many advantage of this Bellman-Ford over the Dijkstra algorithm. So this is the also we can say the same algorithm as Dijkstra, well, but there are two major disadvantage of Dijkstra algorithm. That is first one is we cannot apply that Dijkstra algorithm in negative edges. Also, we cannot find the negative cycle in the graph with the help of Dijkstra algorithm, or we can say. So here comes a Bellman-Ford algorithm. So which is we can say work fine with the negative edge. If we are getting a negative weight edge, so we can so we can find the minimum distance, and also it the first advantage is we can apply this algorithm with the negative edges also, and second advantage is we can what we can say we can help detect the negative cycle with the help of this Bellman-Ford algorithm. So as we are as meanwhile which is that is Dijkstra algorithm is not capable of both the things, that is we cannot apply the negative on the Dijkstra algorithm in Dijkstra algorithm in negative edges, as well as we cannot find the negative cycle in a graph. So this is the say what say we can say how the Bellman-Ford is different from the Dijkstra algorithm. So what we have given in this this test case. So we have given that 6 vertices, so 6 nodes are there, and the source node is 0. So the this input are in the form of, that is the first thing is representing the initial edge, or we can say initial node. So this first edge will be denoting the initial, we can say starting point, or we can say starting point. This is denoting the starting point of the node, and this is denoting the next number is denoting the, we can say, V. So there is an edge from 3 to 2, and which has a weight of 6. So and this third, that is third element will denoting the weight of the edges between the two nodes, that is 3 and 2. So this is denoting the weight. Okay, so 6 is there, we can say. So these are the, we can say, these are the inputs for this 6 node or this this input. So let me first draw this input, so by which we can easily apply the Bellman fault algorithm to find the minimum distance from the source node to the all node. So let me draw the quickly let me draw quickly this let me draw the example of this quickly. So this is node 0. So node 0 to 1, 0 to 1, that is 5, has weight 5, and this is 1. This is 1 is connected with the node 5 with the weight of, we can say, negative weight, that is -3. Okay, another we have to node 2 and node 3. From 5 to 3 the edge weight will be 1, and 3 to 4 the edge weight will be -2, and from 2 to 4 edge weight will be 3, there will be 6, this is -2. So this is the given example, or we can say given input. So we need to find the, this is our source node, that is 0 is our source node, and from 0 to every node we have to find the minimum distance. So let me maintain an array, or we can say array, which will store our the minimum distance of the particular node from that source node. So from 0 to 0, we can say from source to source the distance will be of course 0, and from source to node 1, that is the distance will be 5, and from source to node 2, that will be the distance between this one path will be we can go from 0 to 1, and then from 1 to 2, that will be 3, and another path will be, that is from first will be, that is from we will move from 0 to 1, and then 1 to 5, and then 5 to 3, and then 3 to 6. That means this will be 2, 3 and 9. So 5 will be, we can say, we cost cheaper, 5 will be less, so we will write this 5, and after that node from node 0 to node 3 the weight will be, that is 2 plus 3, that is 3, and for node 4 that is also 3, that is 2, 2, 3, for 0, 0, 1, 2, 3. Okay, node 3, so that will be also 3. So for node 4, that is 2, 2 plus 3, 3 minus 2, that is 1, and for node 5 there will be 2. So this is my given no, sorry, this is my we can say shortest this array will this array, that is, this is distance array. Okay, let's say the name of this array will be distance. So this is distance array, and this will contain our shortest distance, all possible shortest distance from the source node to the all vertices of the graph. So it is denoting the all the minimum distances from the source node to the all the vertices of the graph. So from 0 to 0 the distance will be 0, and size of this distance array will be same as the number of vertices. So this has size 6, that is okay, and from 0 to 0 that is distance 0, and 0 to 5 sorry, 0 to 1 there is 5 distance, and 0 to 2 there are 2 options. From 1, first option will be we can go from 0 to 1, and then 1 to 2, so this will take weight 3, and then another option that has that is from 0 to 1 and 1 to 5 and 5 to 3 and 3 to 2. That will be another option, but it will cost greater, or we can say it will cost more than this, we can say more than this above path. So we will go with this our shortest path. We will go with the above option. So we have written the -3, so sorry 3. So next we will move to the next 4. So this is also which have also weight 3, and for node 4 that is weight 1, and for node 5 that is weight 3. So how we will calculate this? With the help of we can say with the help of the code, or we can say with the help of any approach. So simple approach is, in this algo we what we will do, we will try to the intuition is simply release all the edges of n minus 1, we can say n minus 1 time. Release the intuition is to release all the edges n minus 1 times sequentially, and after n minus 1 iteration we should have minimized distance to every node. So in this algorithm, what we will do, we will simply relax all the edges for n minus 1 iteration. What we will do, we will release n minus 1 nodes for or we can say all the edges. We will relax all the edges for n minus 1 times sequentially, and after n minus 1 iteration we should have the minimized distance to the every node. And this minimizing of distance, minimizing the distance to reach every node is called, we can say, edges, is called relaxing of edges. So minimizing the distance to reach every node, so minimizing the distance to reach every node is called the relaxing of edges. This is called the relaxing of edges. So relaxing of edges means, simply what we are doing is, simply we are exploring two parts. And if I have calculated the first part, and the first part is in the first part the weight is coming, let's say 3, and the another part then after that when I explore the second part, and let's say that has that the weight has come, weight has come 5. So I will take the, we can say, the minimum path that will be called the relaxing of edge. So relaxing of edge is nothing, we is simply we will choose the minimum edge, minimum edge that has minimum weight, minimum we will choose the edge between the nodes that has minimum weight. Okay, so this is the we can say relaxing of edges. So in a graph of n minus 1 nodes, we take we take at most n minus 1 edges. Okay, n minus 1 edges to reach the n minus 1 edges to reach the first node from the last node, to reach the first node from the last node. Okay, and we need n minus 1 iteration. It is impossible to draw a graph that take more than n minus 1 edge. And the another concept is in this problem, we can say algo, is how we can detect the negative cycle in a graph with the help of this bellmon fault algorithm. Uh, so what we will do, when we are doing n minus 1 iteration, we will do another iteration, that is nth iteration, if nth iteration is possible for us to do. So that indicates that there is negative cycle present in the that graph. So we will try to relax the one more edge. What we will do, we will try to relax the one more edge after n minus 1 iteration. Okay, after n minus 1 iteration we will try to relax one more edge, and it is if it is found that and it is found that the relaxation of any edge is possible, so we conclude that there is an absolutely negative cycle in a graph. So there is we can say definitely a negative cycle present in the graph. So the first thing what we are doing is we are relaxing we are relaxing all the edges n minus 1 times. Okay, we are relaxing all the edges n minus 1 times sequentially, where n is the number of nodes, n is denoting the number of nodes, and after n minus 1 that is after n minus 1 after n minus 1 iteration, we should have the minimized distance to every node. Okay, and minimizing the distance to reach every node is called the relaxing of edge. Okay. Okay, so let's directly jump into our that is algorithm, what the algorithm and what are the steps to this algorithm. So let's directly move to the algorithm. So what are the steps, let me tell one by one. So first of all, let me erase this written stuff. So what I will do, I will maintain a distance array that will we can say store our distances from source node, that will store our minimum distance from source node to the every node. Okay, and that distance from source node to source node will be always 0. Okay, because it is in the same position, and the distance from source node to source node will be 0, and we will run a loop for n minus 1 times. Okay, because we are starting with the nth node, so sorry, first node. So we will simply iterate the loop, run, or we can say run the loop for n minus 1 times, and inside that loop we will try to relax every edge. And let's say this is example of our edge, that is u, v, and that will third thing is denoting the we can say weight of the edge. So what we will do this is starting point and this is ending point, and this is the weight between these points. So if our distance of that is u plus weight is coming less than distance of u, then we need to store it in our, that is in our distance vector. Okay, then we need to update the, we can say update our distance vector. So distance vector will be updated with this value, that is u plus weight, that will be, this is u plus weight. Okay, so simply what we will do, let me erase this written stuff. So what we will do, simply we will maintain a distance array that will contain our minimum distance from source node to every node, and from source node to source node we know that the distance will be 0. Okay, and we know that the distance of source node will be 0, and we will try to run a loop from 0 to n minus 1 iteration, because we are started we have already visited this first node. So we are starting from the 0 to v minus 1 iteration, and we will simply, what we will do, this we will we have the given input in the matrix, so we will try to access the, can say column of each matrix, and the first element of that row will be denoting our starting point, and second element will be denoting our end point, and third element will be denoting the weight of the graph, so weight of the edge between the u and v. So and we will check the condition. If our condition is true, we try to simply update the weight. So this is up for the, we can say, Bellman Ford algorithm. So